next talk. This is given by Dr. Radhika from Tata Institute of Fundamental Research. I think Radhika was the last PhD student of Professor Raghunathan. Yeah, it's nice to have her speak in this conference, and she will talk on congruence subgroup problem for groups of inner type AN. So over to you, Radhika. You have 30 minutes.
Yeah, thank you very much. So I'd like to thank the organizers for giving me this opportunity to talk in this conference on the occasion of 80th birthday of Professor Raghunathan. I will take this opportunity to wish him a very happy birthday. So today I'll be talking on Congruence Subgroup Problem for groups of inner type AN. This is a joint work with Professor Raghunathan, which grew out of my doctoral dissertation. The talk is divided into three parts. So we begin with a problem formulation, and we'll glance through some developments of the problem with regard to a conjecture by Sayre. And in particular, we'll be looking at anisotropic groups of inner type AN, which will occupy the latter half of the talk. So let's begin with the problem formulation. We fix a few notations. K will denote the number field. V will be a set of inequivalent valuations of K. BF will denote the non-Archimedean valuations. Infinity will denote the Archimedean valuations. S will always be a proper subset of B, which contains the Archimedean places. OS is a ring of S integers, comprising those elements in K, which are integral outside S. G will denote a linear algebraic group defined over K. I will also occasionally mention it as a K group. We fix an embedding of G in GL and C, so that the ring of S integers is given by the intersection of GK with GL and OS. And for a non-zero ideal A in OS, GA will be the kernel in GOS of the map reduction modulo A. And so it's clear that GA is a subgroup of finite index in GOS. It will be called as a principal congruence subgroup of level A. Now, S congruence, a gamma subgroup of a subgroup gamma of GK will be called an S congruence subgroup if it contains GA for some non-zero ideal A as a subgroup of finite index. Gamma will be an S arithmetic subgroup if it is commensurable with GA for some non-zero ideal A. Now it is important to note that these notions are independent of the embedding that we have chosen. The lemma here asserts precisely the same. So it basically states that under K morphism of K groups, the inverse image of an S congruence subgroup is an S congruence subgroup. Similarly for S arithmetic subgroups. We look at the formulation of the problem given by Sayre, so that we introduce two topologies on GK. One is the S congruence topology, where the fundamental system of neighborhoods of identity is given by the collection of S congruence subgroups. Similarly, one has the S arithmetic topology, and we denote G hat SA as the completion of GK with respect to the arithmetic topology, and G hat SC will denote the completion with respect to congruence topology. And because the S congruence subgroups are arithmetic subgroups, one has that the congruence topology is weaker than the arithmetic topology. This gives a, then the identity map of GK extends to a continuous homomorphism from the arithmetic completion to the congruence completion. It turns out that this map is surjective, giving us the following exact sequence. The kernel of this map is what is known as the S congruence kernel, and by construction, GK embeds into both the completions. So this kernel is split, the sequence is split over GK. And it can be shown that this S congruence kernel is trivial only when the two topologies coincide. That is when the answer to the congruence subgroup problem is affirmative for G. So according to Sayre, the formulation of the congruence subgroup problem is to determine the S congruence kernel for a given S and G. Certain remarks regarding the kernel are in place. We'll need this in the future, in the sequel. So the S congruence kernel is a profinite group. In fact, CS is a functor from the category of K groups to the category of profinite groups. And when S is a subset of S prime, we assume that both S and S prime contains the Archimedean places, then one can show that there exists a natural surjective map from the S-congruence kernel to the S-prime congruence kernel. So this implies that in order to prove the congruence subgroup property for G, it suffices to consider in the cases when S is finite. And the third remark is well known that the computation of the S-congruence kernel for an arbitrary algebraic group G over K can be reduced to that of an absolutely simple, simply connected group. So henceforth, we'll assume that G is absolutely simple, simply connected. And the last remark is that the S-congruence topology on GK coincides with the induced topology of GK under the diagram embodying the group of adelic points. So here AS denotes the algebra of S adel. So it is a restricted product of KV with respect to the ring of integers. And because we assume that G is absolutely simple, simply connected, and S rank G is greater than 0, the strong approximation property holds for G. It basically states that GK is dense in the group of adelic points. So one has the S congruence completion is the whole of the adelic points. Hence, we can rewrite the exact sequence with replacing the S congruence completion with the group of adelic points. Okay, so that is for the formulation. Now we'll move on to see certain developments of the congruence subgroup problem. So in the K isotropic cases, one has fairly complete results for the S congruence, for the congruence subgroup problem. It is summarized in this theorem. Basically states that when G is K isotropic with S rank greater than equal to 2, then the congruence kernel is trivial if S contains a non-complex place. Otherwise, it is the group of roots of unity in K. So special cases here were established in the works of Bas-Milner-Sayre and Meniké. They proved it for SLN and greater than equal to 3. Matsumoto considered split Chevalier groups, whereas Steven considered non-split groups of classical type. And around this time, Sayre also studied the group SL2. So Raghunathan proved it for K rank 1 groups, and he also gave a uniform proof for a general isotropic group. And coming to the anisotropic groups, the first result was given by Nisser for spinor group of F, where F is a quadratic form in more than five or more variables. This was extended to that of classical groups by Tominov and Rapinchuk, and certain exceptional groups were also dealt with by Chernosov, Platonov, and Rapinchuk. So all these developments are given in detail in an exquisite survey article by Raghunathan and also by Rapinchuk. Now we look at the conjecture by Sayre, which is relevant to the congruence subgroup problem. So it basically states that if G is a absolutely almost simple, simply connected K group, and such that G is KB isotropic for all non-Archimedean V in S, then the S congruence kernel is finite if S rank is greater than or equal to 2, and it is infinite if S rank is equal to 1. We will confine ourselves to the case where the congruence kernel is finite, that is when S rank is greater than or equal to 2. And as seen before, this conjecture is completely settled when G is K isotropic. The complement of S is the place is precisely the place where G is KB anisotropic. The Sayre's conjecture is nothing but the Margulis-Platonov conjecture, which gives the normal subgroup structure of GK in this case. So the conjecture states that for every non-central normal subgroup of GK has a form N is delta inverse U, where U is an open normal subgroup of GS naught in the Dale group, and delta is the diagonal embedding of GK in GS naught. So this the Margulis-Platonov conjecture is kind of completely settled for the isotropic case. It coincides with the Nesati's conjecture, which is completely known, and Philip Gill has kind of provided a uniform geometric proof for the same. And in the anisotropic cases also, it is known for many of the groups except the outer type AN, the triality groups D4 and the exception group E6. The contributions here are by Borovoy, Chernosov, Margulis, Platonov, Suri, and Tominov. I have reserved the contribution for inner type AN until the next slide. Okay, Now coming to anisotropic groups of inner type A. These groups can be realized as the known elements of finite dimensional division algebra over K. In this case, the set S naught, where the group remains anisotropic, are precisely those places where the division algebra D tensor KV remains a division algebra. The Margulis has this result that it is a quaternion division algebra over K and G is SL1T, then the MD conjecture holds for GK. This includes all the anisotropic groups of type A1. And now come back to the Margulis-Platonov conjecture. This is also proved for anisotropic K groups of inner type AN by the work of Raghunathan, Rapinchuk, Potapchik, Segev, and Seeds. There have been certain recent developments for the groups of inner type AN with regard to the SAYS conjecture. One is by Prasad and Rapinchuk. For this, we need to state the following definition. If K or K is a Galois extension and sigma is an element in the Galois group, and a generalized arithmetic progression is a set of valuations, non-Archimedean valuations, V in VF such that K is unramified at V and the probability element belongs to the conjugacy class of sigma. And Prasad and Rapinchuk recently proved that if G is K an isotropic algebraic group of inner type AN, and S is a generalized arithmetic progression disjoint from S naught, then the S congruence kernel is central and in fact trivial. My work with Raghunathan also deals with K anisotropic groups of inner type AN, AD-1. So we state that if S has a certain property which we call as being the D-amenable set, such that GKV is non-compact for all non-Archimedean V in S, then the S congruence kernel is trivial. As a corollary, we obtain that the kernel is also trivial in the complement of S is a finite set containing S naught. Now, I'll define what the D-amenable property is. So here D is a positive integer, and let S be a subset of valuations and W be the complement of S. If there exists an integer H greater than 1 such that for every extension K over K of degree T, the quotient KW plus mod K bar star has exponent dividing H, then we say that S has D-amenability property. So here KW plus is the quotient of the W ideals modulo identity component, where W ideals is the restricted product of KV star with regard to the units, and K bar star is the closure of K star in KW plus. One can define the exponent of a D-amenable set S as the GCD of the exponents of KW plus mod K bar star, where K runs, capital K runs over all extensions of degree T. And we show that a generalized arithmetic progression is in fact a D-amenable set. Even if you throw out the Dirichlet density 0 set, it still remains D-amenable. What is desirable is to show that any finite set S containing the Archimedean places and which is disjoint from S naught is D-amenable. Then together with the theorem here, one has the result, one has Say's conjecture for groups of inner type AN, anisotropic groups of inner type AN. Now we look into a few methods of proof. A common strategy of proof seen in many of the anisotropic cases is is that there are two steps. One is to show that the S congruence kernel is central in the arithmetic completion. And once you have the centrality, then it can be shown that the S congruence kernel is a contact interval of the kernel of the map H2GASQ mod C to H2GKQ mod C. Here the left side has continuous cohomology and the right side has a group cohomology. And this kernel is in fact what is called as the metaplastic kernel. And it is known to be finite always. And this metaplastic kernel is completely determined, and hence so is the S congruence kernel when it is finite. So it is shown that the S congruence kernel is either trivial or group of roots of unity. This is dealt with in complete generality in the works of Prasad Rakuchak and Prasad Raghunathan. And there is no standard way of proving the centrality of the S-congruence kernel. However, one method which kind of works for all isotopic groups and also certain anisotopic groups is this is given by this proposition. So that if G is defined over K and such that for every V not in S, there is a subgroup GB of G hat SA of the arithmetic completion such that it maps onto GKV. Remember that the congruence completion, we identify the congruence completion with the group of the adelic points, and GKV sits inside this group GAS. And the next point is for V1 not equal to V2, we need GB1 and GB2 to commute element wise. And the third condition is that the subgroup generated by GB is dense in the arithmetic completion. Then CSG is central in G hat SA. So this result, using this result, Prasad and Radhika in their recent work establishes the centrality of the kernel for G equals SLA and greater than or equal to 3. In fact, in an earlier work, Raghunathan has proved that the same argument can be used to prove centrality of the congruence kernel for K groups with K rank greater than or equal to 2. And Rapanchuk proves this using this result, simplifies the proofs of centrality of some anisotropic exceptional groups in one of his works. Now we look at a proof of our approach to the triviality of this congruence kernel for when SST amenable is slightly different. So here we begin with looking, considering the centralizers of elements of the S-congruence kernel, the centralizers considered in the arithmetic completion. And the crucial point here is the fact that the image of these centralizers maps onto a subgroup of finite index in the congruence completion. So this is the content of the proposition given here. It basically says that when SST amenable with exponent Q, the centralizer has the form omega x times G, the adelic points K, of GKW S0, W minus S0, where omega S is a subgroup of finite index in GK S0. One then considers the abelianized kernel. So going on with the commutator of CSG, one has the following exact sequence. And using the proposition, it can be shown that the centralizer of CSG prime, considering the arithmetic completion mod C, is a subgroup of finite index in the S-congruence completion. Now, this kind of helps us to show that the S-congruence kernel, using the MP conjecture, one shows that this following the given extension here is central, and then from the works of Prasad Raghunathan and Prasad Rakuchak, one can conclude that the kernel here is trivial. So one has that CSG prime is trivial. Yes, and this shows okay. The triviality of CSG prime is that CSG is perfect for S whenever SST amenable. Now the S-congruence kernel is profinite, and if non-trivial, it should admit a finite simple quotient. So we show that the S-congruence, and we prove that the CSG in this case quotient. Hence, one has the result that when SST amenable and S and does not intersect the set S0, the S-congruence kernel is trivial. Okay, I think I'm done here. And here are a couple of references. And the last three are survey articles, which includes which are extensive survey articles. And here, the last two words are the recent developments on groups of inner type AN. And the computation of the metaplastic kernel is given in Raghunathan's paper, Prasad Raghunathan and Prasad Rapic's paper. Yes, I think I'll stop here. Thank you.
Thank you, Radhika. We will take some questions. Please unmute yourself. You can ask questions. Okay, I don't see any questions. So thank you very much, Radhika.
Thank you.
Yeah, we will